Good evening, students. Welcome to today's 12th physics class. Today, we are going to explore some truly fascinating phenomena of light, interference, diffraction, polarization. By the end of this session, you will understand what these terms mean, how they differ, and their practical application in the world around us. Okay. Before we dive in, let me share a quick motivation story. Think about Thomas Young, who in the early 19th century performed his famous double slit experiment. Double slit experiment. At a time when many believed light pure light was purely a particle. Particle. Young's simple yet profound experiment provided combining evidence for the wave nature of light. Okay, revealing that phenomena of interference. So his work completely changed our understanding of light. It shows how a single experiment can reshape scientific thought. Let's carry that spirit of inquiry into our lesson today. All right. So let's get our minds warmed up with a quiz, uh, 3 MCQ. Okay. I'm going to share the screen. Wait. If you know the answer, you can tell me. Okay. Okay. So this is the first question. Which of the following best describes a transverse wave? Which of the following best describes a transverse wave? Option A. The particles of the medium vibrate parallel to the direction of wave propagation. The particles of the medium vibrate perpendicular to the direction of wave propagation. The wave requires a medium to travel. Sound waves are an example of this type of wave. So, which one is the best example for the transverse waves? Yes, two. Okay. PRGJZ. Good. Two. Okay. Anyone? Any other students? Any other schools? Yes. Next one. Yes. GJC. Penumur. Two. Yes. Okay. Good. Okay. Okay. Right. So, yes. Good. APMS. Sick. Kalapuram. Pilam. Okay. Good. Okay. Good. So the particles of the medium, yes, correct. Very good. Vibrate perpendicular to the direction of wave propagation is the best definition for the transverse wave. Okay. Right. Good. Very good responses. Okay. Now we will move into the next question. Second question. What is the relationship between the speed V, frequency F, and wavelength of lambda of wave? Which one? V is equal to F plus lambda, V is equal to F minus lambda, V F into lambda, and fourth one, V is equal to F by lambda. Which one? 3, 3, 4. Okay, 4, 3. Okay, good, good. Okay, 3. Which one is correct? Which one correct? Very good. 3. Okay. MF GJC Kuppam, 2, 3 GJC. Okay, good, good. 3, 4. Which one is correct? 3 or 4 or 2? Which one is correct? Any other responses? Any other school? Any other school? Okay, good. Yes. Okay. KSR room number 1, MSM GJS girls. Very good. 3. Yes. Okay. So the relationship between speed, frequency, wavelength, lambda of the wave is V is equal to F into lambda. Speed is equal to frequency into wavelength. So if you know the frequency and the wavelength of particular light, you can tell that speed of that light. Yes, very good. Great, great, great. Very good. Okay. We will move into the next question. Phenomena is not explained by the wave nature of light. Already you know about that wave nature and particle nature in the wave optics. Okay. So reflection, refraction, photoelectric, and diffraction. So which of the following phenomena is not explained by the wave nature of light? Reflection or refraction, photoelectric effect, 3, 3. Okay, good. Krishnaveni, GJG, Penumur, APRJ, Panavasi. Okay, 3, 3, 3. Yes, okay, good. Photoelectric effect. Yeah. Okay, okay, okay. Good, good. Okay. Photoelectric effect, 3, 3. Very good. Great responses. Okay, super. 3, 3. Okay, super. So, wave nature of light. In that concept, we can prove that reflection, refraction, and diffraction. One phenomena, that is photoelectric effect, is not explained by the wave nature of light, because photoelectric effect explained by the particle nature of light. Okay, good, great. Submit. So we can see the answer. Yes, which of the following is best transverse way? Particles of the medium vibrate perpendicular direction of wave propagation. Relationship between the speed, wavelength, and V is equal to F into lambda. Which of the following phenomena is not explained by the wave nature of light? Photoelectric effect. Great. Very good. Super. Okay. So, I see most of you have super responses. Okay, right. Now, let's introduce our key terms for today. We are focusing on the 3 distinct yet related phenomena of light: interference, diffraction, polarization. Okay. First of all, interference. Interference. Yes. So interference means something like that, interfere. Yeah. So here one calm pond. Imagine you throw 2 stones. Okay. So ripples like that. Yes. The ripples or waves from each stone will spread out and cross each other. In some places, like this, in some places, the crest of the waves will add up, making bigger wave. In some places, the crest, okay, the crest of waves will add up, making bigger wave. In other places, crest might meet a trough and cancel each other out. So crest and trough might meet and cancel each other out. So this mixing of waves is called interference. This mixing of waves is called interference. Light being a wave does the exact same thing. So when two lights wave meet, they can either reinforce each other to create brighter light or cancel each other out to create darkness. Okay, so they can add up or they can cancel out. So if they add up, brighter light; if they cancel out, darkness. So this is the principle of this is the concept, that is principle of superposition. Superposition means just add up. Okay. Okay. I will set a one simulation right now. Yes, crust and trough interference. Very good. Great. So, so here, just look at that. If you throw the two stone or like a little drop, so wave formed. Okay, right. Now, this is a light source. Light waves spread as a wave format. Is it clear? Okay, right. Imagine here two light sources are there. Okay, two light sources are there. So already I told you, light being a wave does the exact same thing of the two stone examples. Yes. So when two light waves meet, they can either reinforce each other to create brighter light or cancel each other out to create darkness. Yes. Now you can see the screen. So here in that screen, you can see the band. One is dark band, another is bright band. Okay, right. This is a interference. This is a interference. Okay. Now we will move into that third tab. So here, okay. So here, a single light sources are there, laser. We shine a single light source onto the barrier with two tiny, so we can change the color. Okay, so for example, okay, so we shine a single light source laser onto the barrier with two tiny parallel slits very close to each other. Yes, is it correct? Okay. The light passes through these slits and acts like two separate synchronous wave sources. Okay, right. So when these waves hit a screen on the other side, we don't see uh, two bright lines. Yeah, when these waves hit a screen on the other side, we don't see two bright lines. Instead, we see a pattern of alternating bright and dark bands called fringes. Okay, like that. So here you can see the bright. So bright fringes are where the waves arrive in synchrons or in phase. and add up. Add up. This is a consecutive interference. Here you can see the dark. This is a bright, this is a dark. So dark fringes are where the waves are out of synchronous or out of phase. They cancel out. So this here cancel out, here add up. So dark fringes is known as destructive interference and bright fringes is known as a constructive interference. Okay. Okay. Clear? This is a interference. So important formula in that interference topic. First one, constructive interference. Already we know that bright fringes. Yeah. So constructive interference. Bright fringes. Path difference, that is y equal to n lambda. Here n is equal to 0, 1, 2. Okay, lambda is a wavelength. This is a path difference. So whether interference is constructive or destructive depends on the path difference. The exact distance one wave travels compared to the other is called as path difference. So path difference means the exact distance one wave travels compared to the other. So whether the interference is constructive or destructive depends on the path difference. Okay, this is the important formula for constructive interference. For the destructive interference, y is equal to n plus 1 by 2 lambda. Here also n is equal to 0, 1, 2, 3, something. Okay, it's going on. So n means order of the fringes, first order, second order, like that. Okay, so n plus 1 by 2 into lambda, which is y for the destructive interference. Okay, now another one important formula, fringe width, that is beta. Fringe width, that is beta. Fringe width means the distance between two consecutive bright or two consecutive dark fringes. So here one bright and dark and one bright and dark. So the distance between two consecutive bright or distance between two consecutive dark fringes is known as a fringe width. So beta is equal to lambda into d by small d. Okay. So here lambda is the wavelength of light. D is the distance to the screen. So this is a slit, this is a screen. So this is a D, distance to the screen. And small d is the distance between the slits. Already we know that here one slit, yes, like that. So distance small d is known as the distance between the slits. So this fringe width formula is super important. It tells us that pattern spread out if you use a longer wavelength like red light, or if you move the screen further away. Okay, the pattern spread out if you use the longer wavelength like a light, or if you move the screen further away, because small d and capital D. So capital D increases, beta increases, lambda increases, beta increases, small d increases, beta decreases. This is all belongs to interference. Okay. Now diffraction. Have you ever noticed how sound can travel around corners? Sound travel around corners. You can hear someone talking in the next room even if you can't see them. Yeah. This bending of waves as they pass through the opening or around an obstacle is called diffraction. Okay. So bending of waves. For example, a light wave or sound wave. Okay. Bending of waves around as they pass through the opening or small obstacle. Okay. A small hole opening or around an obstacle is called as diffraction. Light does this too. When light passes through very narrow opening, it may be called as aperture or slit. Okay, it spread out instead of traveling in a straight line. Okay, so when light passes through the very narrow opening, like for example slit or aperture, it spread out instead of traveling in a straight line, because light travels in a straight line is the important characteristics of the light. But here, diffraction. So in the diffraction concept, light behaves something other than travels in a straight line. The smaller the opening, the more the light spreads. The smaller the opening, the more the light spread. So this is a clear proof that light behaves like a wave. Okay, this is a clear proof. Okay, so I will share the screen again. Okay, right. So let's look at what happens when light passes through the single narrow slit or single opening. Okay, so here you can see that just like in the double slit experiment, we see a pattern on the screen. Yes, but this time it is very bright and wide central maximum. Yes, this time it's very bright and wide central maximum with much dimmer and narrower bright fringes on either side, separated by the dark areas. Correct? You can change the shape of the hole like that, or like that, or like that, or like that. So in that cases, you can change the diameter of that circle. So here you can see the uh, like 16 holes, yeah, 16 circles. So now I will change the diameter. You can see the pattern like that, because light waves around the obstacle or a small opening is spread out. Yeah, this is the concept behind that diffraction, like that. And the same also. So smaller the opening, light spread out high. Yeah. So this is a diffraction method. Okay, this is a diffraction method. So here important formulas. Dark fringes. So condition for dark fringes are also called as minima. A sin theta equal to n lambda. Condition for dark fringes or condition for minima. Okay. The dark areas, that is minima, are created when different parts of the light wave from within the single slit interfere destructively. Okay. The dark areas are created because when different parts of the light wave from within the single slit interfere destructively. Okay. So A sin theta is equal to n lambda. And for the central maximum, we can calculate the angular width. So angular width of central maximum 2 theta is approximately equal to 2 lambda by A. So here n plus or minus 1 plus or minus 2. A means slit width and theta means angle to the minimum. So angular width of the center maximum 2 theta is equal to approximately 2 lambda by A. This shows a central bright band is twice as wide as the other bright bands. Okay. You can compare the central bright band with the other bright band. You can see that central bright band is twice as wide as the other bright bands. Okay. So in interference, we have two sources. In diffraction, we are looking at the effect of waves from different parts of the same wavefront. Okay. Next one, polarization. So light is a transverse wave. Already you know that, which means its oscillations are perpendicular to the direction it is traveling. Yeah. It means light is a transverse wave, which means its oscillations are perpendicular to the direction it's traveling. Imagine a wave on a rope. You can shake it up and down, side to side, or any other direction, as long as it's perpendicular to the rope. Clear? Natural light from the sun or bulb is unpolarized light. So unpolarized means its waves oscillate in all possible directions. Unpolarized means its wave oscillate in all possible directions. Polarization is the process of restricting these oscillation to just one plane. So this is unpolarized light. Waves oscillate in all possible direction. Polarization is the process of restricting these oscillating to just one plane. The result is polarized lights. Polarized lights. Okay. Like think of it like passing a rope through the picket fence. If you shake the rope vertically, the wave passes through a vertical slide. But if you shake it horizontally, the wave gets blocked. The fence acts as a polarizer. Okay. So I will share the screen. Another one experiment related to the interference. Polarization. Yes. Yeah. Okay. So here you can see that. So unpolarized line coming. Yeah. So here 3 slits are there. So this is a polarization light. Okay. So this is a simulation intended to help visualize polarization. A polarizing filter has a particular transmission axis that allows only light wave aligned with the axis to pass through. So in this simulation, unpolarized waves passes through the vertical slit, leaving only their vertical compounds. Here you can see that. Leaving only their vertical compounds. So this vertical transverse wave approach a vertical slit. If the slit rotated like that, you can see that. If the slit rotated like that, what did you see? Okay. If the slit is rotated, only component of the wave can pass through. If the slit is rotated 90-degree, the wave is stopped completely. Yeah, wave stopped completely. Clear? So this is a polarization light. Polarization of light. Okay. So here also important formulas. We use here special filters called polarizer to polarize light. Sunglasses, camera filters, and some LCD screens use this technology. When unpolarized light passes through the polarizer, its intensity cut. Okay, intensity is cut in half. When unpolarized light passes through the polarizer, its intensity is cut in half. That means I is equal to I naught by 2. So I naught means intensity of the unpolarized light. What happens if we put a second polarizer called analyzer in front of the first? The amount of light that gets through the depends on the angle between the two polarizers. So this relationship is described the Malus law. Malus law. Okay. Also known as the polarization formula. I is equal to I naught cos square theta, where I naught is the intensity of light entering the second polarizer, and I is the final intensity. Okay. I naught is the intensity of light entering the second polarizer, and I is the final intensity. So if the polarizers are aligned like that, theta is equal to 0 degree, all the light gets through. So I is equal to I naught. Yeah, if you put the cos 0, 1, so I is equal to I naught. If they crossed like that, 90-degree, no light gets through. Already we saw that. Yeah. So in that case, I is equal to 0 because cos 90 is 0, 0 anything 0. So it becomes dark. This is how some 3D movie glasses work. Clear? Okay. So interference is the superposition of two waves creating bright and dark fringes. Diffraction is the bending and the splitting of waves as it passes through the small opening. Polarization is the filtering of light waves to make them oscillate in a single plane. Clear? They are the heart of technology like holography, fiber optics, and the LCD displays. Okay, right. Now we will move into the numeric problems. Okay, I will once again. So okay, else already I showed that diffraction, interference, and polarization. Okay, right. So we have seen the concept visually also. Yeah, let's apply them to some numerical problems, especially concerning interference patterns. I will solve two problems on the whiteboard. Okay. Problem number 1. In a young double slit experiment, so which is known as a YDSE. Yeah, Young's double slit experiment. The distance between the distance between the slits is 0.5 millimeter. Okay. and the screen is placed at a distance of 1.5 meter from the slit. Wavelength of light 600 nanometer. Then calculate the fringe width. So this is the first problem I will solve. Okay. So in a Young's double slit experiment, the distance between the slit is 0.5 millimeter and the screen is placed at a distance of 1.5 meter from the slits. If the wavelength of your light is used 600 nanometer, then find the fringe width. Okay. So solution, given data, D, small d, 0.5 millimeter. Yeah. So 0.5 millimeter means 0.5 into 10 power minus 3 meter. We have to convert into meter, basic units. Okay. Capital D, screen distance 1.5 meter. Lambda 600 nanometer. So nano means 10 power minus 9. Yeah. 10 power minus 9 here, meter also. Okay. So we have to find fringe width. So we know the formula beta lambda d by small d. Is it correct? Okay, good. We can put that value 600 into 10 power minus 9 and capital D 1.5 and by small d 0.5 into 10 power minus 3. Okay. So here 600 into 1.5, 900. And 10 power minus 9 by 0.5 into 10 power minus 3. So 900 by 0.5 and 10 power minus 3 goes there and 10 power 6. Okay. So 900 by 0.5, 1800 into 10 power minus 6 meter. We can change into the some other units like a millimeter or a meter. Okay. So in that case, .8 and 10 power minus 3 meter. We can change this value like this. Yeah. 1800 into 10 power minus 6 meter, which is equal to 1.8 into 10 power minus 3 meter or 1.8 10 power minus 3 meter means millimeter. So 1.8 millimeter. Is it correct? Very good. Clear? This is a solution for the first problem. Okay, note it down. I will write the second problem now. So here 1.8 millimeter means fringe width. That is the distance between the two consecutive bright or two consecutive dark fringes will be 1.8 millimeters. We have to understand the concept. So here beta means fringe width. Okay. So that means the distance between the two consecutive bright or two consecutive dark fringes. 1.8 millimeters. Okay, right. So next sum. Problem number 2. A double slit experiment, a double slit experiment uses light of wavelength 600 nanometer. Slits are 0.2 millimeter apart. And the screen is 1.5 meter away. So calculate the distance between the central maximum and the first bright fringe. Another one very important problem. A double slit experiment uses light of wavelength 600 nanometer. The slits are 0.2 millimeter apart and the screen is 1.5 meter away. Okay, now we have to find the distance between the central maximum and the first bright fringe. Okay, right. So the given data lambda equal to 600 nanometer, 600 into 10 power minus 9 meter. Small d 0.2 millimeter. So 0.2 into 10 power minus 3 meter. Capital D 1.5 meter. Yeah. So the difference between the distance between the central and some other point, that is first bright fringe or second bright fringe or first dark fringe, like that. So we have to put y equal to n into lambda d by small d. So we have to put subscript n. So n means nth bright fringe or so here is a formula for only for bright fringes. Okay. So this is a formula for the position of bright fringes in double slit experiment. In that case, we have to put 1 or 2 here in that cases, like there for first bright order or second bright order. In that case, for the second bright order, we have to put 2. For the third, we have to put n is equal to 3. Already we know that what is lambda d and small d. Okay. So lambda 600 into 10 power minus 9. Small d and capital D 0.2 into 10 power minus 3. Okay. 900. 600 into 1.5, 900. Okay. We know that. Okay. By 0.2 into 10 power minus 3. Yeah. So this is for y1. Okay. N is equal to 1 in that case, in this problem. Okay. So y is equal to 1. Sorry, n is equal to 1. So y1. y1 is equal to already n is equal to 1. So y1 is equal to 600, like that. Okay. y1 equal to 4500 by 10 power minus 6 meter. So we can change like that, 4.5 into 10 power minus 3 meter or 4.5 millimeter. So this is a answer for that second question. So we here the distance between the central maximum and the first bright fringe is 4.5 millimeter. Again, we use the same formula as the first bright fringe is essentially one fringe with away from the central maximum. Okay. Right? Okay. Good. Excellent work on those problems. Now it's time for a short quiz to check your understanding of today's concept. This is a 5 question MCQ quiz on interference, diffraction, and polarization. I will share the screen. Okay. Okay. Right. First question. In double slit experiment, if the distance between the slit is increased, what happens to the fringe width? In a double slit experiment, if the distance between the slits is increased, what happens to fringe width? DS mean double slit experiment. Okay. Degrees all the above. A 443 increases. Okay. Okay. A 4. Okay. 432. Okay. Right. Increases, decreases all the above. 1. Okay. So in the Young's double slit experiment, the distance between the slits, already we know that small d. Yeah. Distance between the small d. And what is the formula of fringe width? Already I saw two problems. Yeah. So beta. Yeah. Then it decreases 3, 1, 3, A. Okay. A lot of students. It increases. Okay. Okay. So, okay. I will choose the option 1. Okay. Right. Second question. Diffraction is the phenomena of which one is correct? Bending of light around the corners of obstacle aperture, superposition of two or more waves, splitting of white light into its concentric colors, reflection of light from the smooth surface. Which one is correct? For the second question, one. Oh, okay. This is okay. Yeah. Very good. Yes. A. Diffraction is the phenomenon of bending of light around the corners of an obstacle or aperture. Very good. Okay. But for the first one, you have to think about it. Okay, right. For the third question, which of the following describe unpolarized light? Light wave oscillating in one plane, light waves oscillating in all possible planes perpendicular to the direction of propagation, light waves that have okay, kindly vote the poll regarding that simulation or activity. Yes, thank you so much. Okay, okay, good. Thank you. Okay, let's get back into that MCQ. Which of the following describes the unpolarized light? Which one is correct? A, 2. Okay, 2. Okay, okay, Okay. So for the third question, okay, third, yes, third question. Which of the following describes unpolarized light? B, 2. Yes. Okay. Light waves oscillating in all possible planes perpendicular to the direction of propagation. Okay. And fourth one, which phenomena is responsible for the colors observed in a soap bubble? Very important and a very interesting question. For that fourth question, 3B. 3B, 3B. Yeah, yeah. Okay. For that fourth question, 2B, 3. Okay, 3. Already we saw that soap bubble. In the soap bubble, you can see the colors pattern. But what is the reason? What is the physics concept in there? Diffraction, refraction, interference, polarization. For the fourth question, refraction, okay, 4A, B, okay, 4, 3, 3, okay. Diffraction, refraction, interference, polarization. Okay. Some of the responses indicating refraction. Okay. 2, 2. Okay. So for your convenience, I will choose the second option, but you have to think. Okay, right. So when light passes through the Polaroid, its intensity is reduced because the Polaroid absorbs all incident light. The Polaroid only allows light waves oscillating a specific plane to pass through. The Polaroid scatters the light in all directions. The Polaroid reflects the light back to the source. Already we discussed about that Polaroid, polarizer. Yeah. So suppose one unpolarized light, for example, sunlight or bulb light, it then passes through that Polaroid, that is also known as a polarizer. What will happen? Its intensity cut. But why? Because D, okay, D2, okay, okay, B, C, okay, C. Yeah, which one is correct? D, 3 or 2 or 1? 2, 4, 2, 4, D, C. Okay, right. So for your so many of the schools choosing third option. So I will choose the third one. But you have to think about it. Okay, submit. Now you can see that answer. In double slit experiment, if the distance already I told you that is fringe width beta is equal to lambda into d by capital D by small d. So small d increases, beta decreases. Yeah. So decreases is the answer. Okay. For the first question. Okay. Note it down. Note it down. Okay. Okay. Second question. Difference is a phenomenon of yes. Bending of light around the corners of obstacle or aperture. Okay, super. For third one, which of the following describe unpolarized light? Light waves oscillate in all possible planes. For example, sunlight or bulb light, perpendicular direction of propagation. Yeah, this is a unpolarized light. Okay. For this question, which phenomenon is responsible for colors observed in soap bubble? Many of the schools are like telling that refraction, but it is because of interference. Interference means interference. Okay, interfere of that two waves, two light waves in the soap bubble, in the thin bubble. Okay, like so there is a layer, upper layer, bottom layer. So sunlight refract and reflect, refraction and reflection, and then interfere. Then only we can see that colors due to the interference. Okay. Okay. And fifth one, when light passes through the Polaroid, its intensity is reduced because many of the schools told that the Polaroid scatters the light in all directions. No. The second answer, the Polaroid only allows light waves oscillate in the specific plane to pass through. Okay. This is the answers. Okay. Yeah. Good. Okay. So we have covered a lot today. Let's make it interactive now. Can 2, 3 volunteers explain one of the concepts we discussed? Perhaps how polarized light, polarized sunglasses work, or how diffraction affects light from the distant street lamp, or even what the different patterns of interference mean. You can tell about anything, any one concept. Like for example, you can say that concept of diffraction, interference, or polarization. All right. So let's quickly summarize what we learned today. So we defined interference as the superposition of waves leading to the constructive or destructive patterns. We discussed the diffraction as the bending of waves around the obstacles or through openings. Yeah. And we explored the polarization. So which is the restriction of wave vibration to the single plane. Okay. For homework, I am imagining two problems that will help you practice this concept and think about their real world implications. Okay. So homework, first one, explain why the sky appears polarized when viewed through, yeah, kindly vote that poll. I will write that homework. Okay. So when viewed through the polarized, okay, polarized sunglasses at a 90-degree angle to the sun. Write a 100-word explanation. Explain why the sky appears polarized when viewed through the polarized sunglasses at a 90-degree angle to the sun. Second question. In a double slit experiment, so DSE, double slit experiment, if the wavelength of light is 500 nanometer, slit separation is 0.15 millimeter. And the screen is 2 meter away. Calculate the, for this question, calculate the distance between first and second bright fringes. Okay. So for that, this question, calculate the distance between 1 and 2. That means first and second. Okay. Bright fringes. Please write down these problems from this whiteboard. We will discuss them in our If you don't know the answer, we will discuss them in our next class. Okay. First problem, first homework, explain why the sky appears polarized when viewed through the polarized sunglasses at a 90-degree angle to the sun. And the second one, in a double slit experiment, if the wavelength of light is 500 nanometer, slit separation is 0.15 millimeter and the screen is 2 meter away. Calculate the distance between the first and second bright fringes. Okay, any questions? Any questions? Okay. Thank you all for your active participation today. Keep observing the amazing phenomena of light all around you. Thank you, teachers, and thank you, students. See you the next time. Jai Bharat, Jai Hind, Jai Vidyasakti.